when we have for instance, x to the 5th times x squared. We're going to learn a formula today that in order to multiply two things that have the same base but different exponents, when we're multiplying these things, we keep the base the same and we add the exponents. So x to the 5th times x squared would be x to the 5 plus 2, which would be x to the 7th. Let's talk for a minute about why this works. X to the 5th would be x times x times x times x times x times x squared. X squared is x times x. And just because there's a times here, that doesn't make it any different than all of these being multiplied together. It's just like we have times in there. And we can see that all that is multiplying a total of 1, 2, 3, 4, 5, 6, 7. X times itself a total of 7 times with a listed factor 7 times. That is x to the 7th. Forget about x's for a moment. Let's say instead of the x's, we had 2's. Let's say we had 2 cubed times 2 squared. Here, if we use the formula we just learned, since we're multiplying two things together that have the same base, we add the exponents. And 3 plus 2 is 5, so 2 to the 5th. So our formula tells us that it would be 2 to the 5th. 2 times 2 times 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. So 2 to the 5th, 32. 2 cubed is 8 times 2 squared is 4. 8 times 4, 32. So we do get the same answer because it is the same thing. The difference is when we have x's, we can't simplify, say, x cubed to a number like 8. And we can't simplify x squared to a number like 4. So we can't just do 8 times 4 is 32. We would have to know that we can add the exponents. Or we can think about it in terms of what the exponents mean. 3 of them times 2 of them is the definition of 5 of them. So we add the exponents when we're multiplying same base. We can't, if this was x cubed plus x squared, we can't do anything here. These are not like terms, so we cannot add them. This is a rule that we can do when we're multiplying bases. Adding bases with the same base and different exponents can't be done, because that's the definition of adding unlike terms. You can't do it. What about if we were dividing? What if we had x to the 6th divided by x squared? Well, here, our rule is going to be that we subtract the exponents. Top minus bottom. Not big minus small, top minus bottom. And then 6 minus 2 is 4. So x to the 6th over x squared, x to the 6th divided by x squared, would be x to the 4th. Now this makes sense, this subtracting rule. I want to change away from x's because when I show you this, I'm going to cross some stuff out. So let's use a's. Let's say we had a to the 7th divided by a to the 5th. The rule we just learned said that we would subtract the exponents. Top minus bottom, first minus second. Because when we see this divided by, we know that's just like a fraction. The first thing is the top, the second thing is the bottom. And we subtract top minus bottom. 7 minus 2 is 5. Or sorry, 7 minus 5 is 2. Here's the thing about math. When you start knowing what's going on, when you get to the point where the rule just clicks and you get it, it's sometimes hard to stop your mind from going to the next step. So when you work with these, you're going to get to the point where when you see a to the 7th over a to the 5th, eventually you're not going to have to think 7 minus 5 is 2. It's just going to come to you, and that 2 is going to be there. You're just going to know that's what to do, but that comes with practice. So that's what happened here. When I was rewriting a to the 7 minus 5, I was already on the 2, and the 2 came out my pen. So I said I was doing this with a's instead of x's to show you, and I was going to cross things out. A to the 7th, that's 1, 2, 3, 4, 5, 6, 7 factors of a. On the bottom, a to the 5th, 1, 2, 3, 4, 5. When everything's written as factors on the top and on the bottom, just like reducing a fraction, if we wrote out the prime factorization on the top and the prime factorization out on the bottom, and then canceled common things from the top and the bottom, we would end up with the fully simplified fraction. This is why it's important to know how to work with fractions, because the rules are all the same. It's just instead of numbers, we're going to have letters. We're going to have variables. This is no different than reducing a fraction. 1 set of a's cancel. 2 set of a's cancel. 3 set of a's cancel. 4 set of a's cancel. 5 set of a's cancel. There's nothing left on the bottom, so we got all the way down to the times 1. On the top, a times a. A times a is a squared. A squared over 1, since everything canceled on the bottom, that's just a squared. There we go. But Even though we can do it by thinking it out like this, that takes time. We need to work on doing things faster and know it well enough to be able to do it faster. So we just use our formula when we're dividing the same base. We subtract the exponents, first minus second, top minus bottom. Let's take a look at this next. X cubed to the fourth power. Here, our rule is going to be to multiply the exponents together. And 3 times 4 would give us 12. So this is an x to the 7th. This is x to the 12th. Why does this work? Well, let me show it again with some smaller numbers, and then we'll use those smaller numbers to draw it out, just like we did the add the exponents rule and the subtract the exponents rule for multiplying and dividing bases. Let's use a squared cubed. What this would be, since a squared is a times a, is a times a cubed. But cubing something means writing it times itself a bunch of times, the number of times of the exponent. So a times a cubed is a times a times a times a times a times a. Did I really just say a times a times a times a times a times a? I sure did. Doesn't matter what order we multiply if it's all multiplication. So in essence, this is 1, 2, 3, 4, 5, 6 A's all together, which is the definition of a to the 6th, which is what we get when we multiply 2 times 3. And you know how we can multiply in any order, right? Well, watch this. 2 times 3 would be the same as 3 times 2. So we should get the exact same answer for a cubed squared. And that makes sense because it's a times a times a squared, a cubed squared, which would be a times a times a times itself, which is a total of 6 A's, a to the 6th. So when we have a power raised to a power, we multiply the exponents. Our next rule, I'm going to follow up with an absolutely never rule. If we have AB squared, the rule here is going to be that we can give the squared to both of the things, A squared, B squared. But here's the never rule. It only works with multiplication. It never works with addition or subtraction. So it's even good with division. If we have A over B squared, we can give the square to the top and the square to the bottom. It's good with multiplication and division, but never addition and subtraction. A plus B squared is absolutely never A squared plus B squared. Never. And we're going to talk about why in a later lecture. But this is not a rule. That square, or sorry, that plus there inside the exponent, no. We can't just give it to both things. But if we're multiplying, if we're dividing, it's all good, man. It's all good, man. I feel I put too much emphasis on the actual words there. So we've gone and done 5 properties. So now I'm going to give you the names so we can summarize the properties that we've gone over. The first thing we did, the fact that B, our base to the M times B to the N, is adding the exponents, B plus N. Since we do this when we have a product, when we're multiplying, this is called the product rule. So the product rule is that we add the exponents. The quotient rule, B to the M over B to the N, B to the M divided by, we're taking the quotient, is B to the M minus N, top minus bottom. So the power rule, sorry, product rule, I just did that thing where I said the next one. The quotient rule, and if we have our base raised to a power and that raised to another power, we multiply those together, B to the M times N. This one's called the power rule. Those are our 3 basic ones. And then we had 2 additional ones that are kind of like the power rule, but it's power of a product and power of a quotient. A times B to the M. So 2 different bases multiplied together, and we're taking a power. We're taking a power of a product, and we give the power to both. And then the other one, where we're taking the power of a quotient, A to the M over B to the M. That's the power of a quotient. But again, the names don't really matter. What matters is being able to work with exponents when we are multiplying bases, dividing bases, taking bases raised to powers to other powers, taking powers of products, powers of things multiplied together, and powers of quotients, powers of things that are divided. So everything I've shown really only works with positive numbers. However, negative numbers also can be exponents. But, and I will write this down, negative numbers do not have anything to do with negative exponents. Negative numbers do not come from negative exponents. A negative number will not give you a negative exponent necessarily. So what's the mistake I'm trying to avoid by driving this home? That's really what you should care about. The mistake I'm trying to have you avoid is saying, for instance, that 2 to the negative 2 is negative 4, because 2 to the negative 2 is not negative 4. You can't just do 2 squared is 4 and make it negative because it's a negative number. No way, no how, never. That is almost as bad as saying a plus b squared is a squared plus b squared, because this is also never, it is not equal. That only works when we are multiplying or dividing, never when we're adding or subtracting. Never. People are still going to miss that. And when I get the email that says, hey, why did I miss this one? I'm going to screen cap that and send it. And I will say that is why it is wrong. So what are negative exponents? Well, if raising something to the first power is itself, and that's where all exponent problems kind of start, the fact that a single thing is an exponent of 1, we should talk about what b to the negative 1 is. And the negative 1 power is actually the reciprocal. B to the negative first is 1 over b. Specifically, it's 1 over b to the first. So a negative exponent is actually a 1 over. If it's already a part of a fraction, a negative exponent on the top would move you to the bottom as a positive, because reciprocal of a fraction means flip. So if you have a negative exponent in a fraction, you would flip it and then divide. But then a whole mess of multiplication and division rules just makes it so things from the top ended up on the bottom with a positive. So we just skip to that. So I probably just lost you. I'm going to bring you back. Don't worry. Let's practice. When we see b to the negative 2, we're going to go 1 over b to the positive 2. That's what negative exponents are. It has nothing to do with a negative number. The only way you're going to get a negative number is if it was already some sort of negative problem. If I had the opposite of b to the negative 2 with parentheses, well, that would be the opposite of 1 over b squared. That would give me a negative, but it's because I'm indicating from the very beginning I want a negative. It has nothing to do with that negative exponent. So that's what I mean when I say negative numbers have nothing to do with negative exponents. I'm going to jump back to positive exponents for a second. I want to refresh on what we do when we have something raised to, for instance, a fourth power, but that thing is negative. Since this negative is inside the parentheses, that is part of the thing that gets multiplied every time. And since there's an even number of these and a negative times a negative works out to a positive, here, positive 4 times positive 4, we're going to get a positive answer. So negative 2 to the 4th with parentheses is positive 16. But if we didn't have the parentheses, that's going to change the answer. Negative 2 to the 4th is like negative 1 times 2 to the 4th. The opposite of 2 to the 4th. Negative 1 times 2 to the 4th. Negative 1 times positive 16. Negative 16. Cubes don't have that same problem. If this was negative 2 cubed or any other odd power, that would be negative 1 times 2 cubed, negative 1 times 8, negative 8. But if I put the parentheses in with the odd exponent, negative 2 cubed would be negative 2 times negative 2 times negative 2. Here there's an odd number, so no matter how many groups turn positive, there will always be another negative left over to turn it back into a negative. So parentheses, no parentheses for cubes or other odd numbers, 5th power, 7th power, 1st power even. It doesn't matter, you're going to get a negative answer. Even powers, the parentheses or the lack of parentheses make a big difference. So same thing with the negative exponents. This negative not being in parentheses with the 2 is telling us that we want the opposite of 2 to the negative 4th, or negative 1 times 2 to the negative 4, which would be a negative on the outside of 1 over 2 to the positive 4th. Because a negative exponent is 1 over. So this would be negative 1/16. But if the parentheses were in before the negative and includes before the negative, includes the whole negative in the base raised to the negative power, a negative power, this whole thing, 1 over, it would be the whole negative 2 to the positive 4 power. But written like this, negative 2 to the 4th is positive 16. So this negative number has nothing to do, this negative exponent has nothing to do with whether or not this is a positive or negative number. That still comes from whether there are parentheses or not, whether we have an even exponent or not. A negative exponent is just 1 over whatever else we have. We've talked about positive exponents. We've talked about negative exponents and what comes right in the middle of negative and positive. 0. So now we should ask, what is anything to the 0 power? And the answer to that question is positive 1. Anything to the 0 is 1. So 3 to the 0 would be 1. What's x to the 0? 1. What's 5x in parentheses to the 0? Well, this is something to the 0 power. So it's 1. What about without parentheses, though? This is where things get weird when we don't have parentheses around the whole base. 5x to the 0 without parentheses. The exponent goes first. The exponent is only attached to the x. So this is 5 times x to the 0, which is 5 times 1, which is 5. X to the 0 isn't the same as multiplying by 0, it's multiplying by 1. So if we have 3x to the 0, that's 3 times 1. That's 3. If we had negative 2x to the 0, that's negative 2 times 1. That's negative 2. One more, if we had negative x to the 0, just negative x to the 0. Since x to the 0 is 1, negative 1. Here we have x cubed times x to the negative 4th. We are multiplying two things together. They have the same base, so we add the exponents, and the exponents are 3 and negative 4. So we add 3 plus negative 4. That's the same as x to the 3 minus 4. If you need that step, you might be going from there. That's fine. 3 minus 4 is negative 1. Anytime we get an answer with a negative exponent, we need to look at the directions, because chances are it says write your answer with positive exponents only, which means we can't leave it as x to the negative 1. We would need to change it to 1 over x to the positive 1, 1 over x. And again, negative 1 itself as an exponent means reciprocal. X as a fraction, x as a fraction would be put it over 1. So what's the reciprocal of x? Flip it. The reciprocal of x is 1 over x. This means if we had 2/3 and we wanted the negative 1 power, that's the reciprocal. 3 halves. A -1 power with a fraction just flips it. And here's why. Let's do 2/3 to the -1. And instead of just flipping it, let's use the power of a quotient rule. This is 2 to the -1 over 3 to the -1. This isn't where we would then subtract exponents. We can only do that when the bases are the same. But what do we know here? We know that writing this as a fraction is the same as having a division problem. 2 to the -1 divided by 3 to the -1. 2 to the -1 would be 1 over 2. 3 to the -1 would be 1 over 3. Dividing by a fraction is multiplying by the reciprocal, and 1/2 times by the reciprocal, just flip it. 1 times 3 is 3. 2 times 1 is 2. 3 halves. That's why it's just flip the fraction. Why would you do all that work every time when you don't need to? Things from the top go to the bottom. Things from the bottom go to the top. And instead of -1 power, we'd have 1 power. So if we had a to the -3rd over b to the -2, this a to the -3 on the top is going to become an a to the +3 on the bottom. B to the -2 on the bottom is going to become b to the +2 on top. If you understand that, fantastic. If you don't understand why, but you understand this, don't think about it too hard, too hard. Don't. Because it boils down to this. This is what you need to know. You don't need to know why it works. You just need to know it does. Why are the rules important? Let's say we have 2 a to the 7th, b to the -4th, all to the 3rd, over 4 a cubed b to the -2, all squared. There are multiple paths to get you to the correct final answer here. There's no correct order to do any of these rules in, but if you keep doing correct things until there's nothing else left to do, you will get to your answer eventually. So I'm just going to start a path and I'm going to go down it. I'm just going to keep finding things to do. Inside the parentheses, there is nothing I can do. I can't add or subtract the exponents because none of the bases are the same. But on both the top and the bottom, I do have a bunch of factors. I have a product, and it's raised to a power. So we have here 2 cubed. So the first factor is 2. We have a to the 7th cubed. And we have b to the negative fourth cubed. Oops. Hang on, I'm going to rewrite that. I didn't leave myself enough room. I apologize. So 2 cubed, a to the 7th cubed, b to the negative 4th cubed. It's about time to change that blue marker. And on the bottom, the squared would go to each of the factors. So 4 squared, a cubed squared, and b to the negative 2 squared. And giving the cube to everything on top, giving the square to everything on the bottom, that has given me more things to do. Don't forget, when you have a number in front of the variables, if the number's inside the parentheses and the variable's outside and it's all multiplication and you're applying this rule, don't forget to cube the 2. Don't forget to square the 4. I'm going to give myself more room by just going back and forth on the steps here. So you'll just keep writing it as another thing, down, down, down. 2 cubed is 8. Here we multiply the exponents. 7 times 3 is 21. Here we multiply the exponents. Negative 4 times 3 is negative 12. B to the negative 12. On the bottom, 4 squared is 16. A cubed squared, 3 times 2 is 6. A to the 6th. Negative 2 times 2, that's negative 4. B to the negative 4. If I simplify, 8 over 16, that's 1/2. And then we can divide our a's by subtracting the exponents. 21 minus 6. And then our b's, we can do the same thing. If you're not going to do anything with the negative exponents first, you have to be careful. I'm going to show this a couple different ways. B is the base. The top is negative 12, and then we are subtracting negative 4. So this is 1/2 a to the 15, 21 minus 6. B, the b is to the negative 12 minus a negative is plus 4. Negative 12 plus 4, that's negative 8. Now, this would be an okay answer, except we're told right answer using positive exponents only. So that means we can't have a b to the negative 8th. This is going to be 1/2 a to the 15th times 1 over, oh boy, sorry. This is going to be 1/2 a to the 15th 1 over b to the 8th. And if we wanted to write this as a single fraction, 1/2 times a to the 15 over 1 times 1 over b to the 8th. Multiply across the top. 1 times 1 is 1 times a to the 15th is just a to the 15th. 2 times 1 is 2 times b to the 8th, 2b to the 8th. A to the 15th over 2b to the 8th would be the final answer. I'm going to show another way to get here. It doesn't use the formulas. It's a little more conceptual, but you might find it easier. And we're going to go back from this step again. So back from where we were here, we can take a step and turn all of the negatives into positives up front. We might have something to deal with again later on, but for now, it'll be up front. Those don't change, but a b to the negative 12 on top would be a b to the positive 12 on the bottom. A b to the negative 4th on the bottom could be a b to the 4th on top. Now, if we have a fraction, reduce it. 8 over 16, 1/2. I'm going to leave it as one big fraction. And I'm going to ask myself for every variable, how many more where? So for the A's, how many more and where? I have 21 on top. I have 6 on the bottom. I have 15 more on top. 21 minus 6, 15. Where? I have more on top, 15 more on top. The B's, how many more where? 4 on the top, 12 on the bottom. I have 8 more on the bottom, 12 minus 4, but on the bottom. 1 times anything is itself, and the bottom 2b to the 8th. So there's a way you can do it as well. In fact, anytime you can use any rule, any logic we worked on in this lecture. If it is correct, you can do it. There's nothing wrong unless it's actually a wrong thing to do mathematically. And if you string together enough correct things, eventually you'll simplify it all the way. Write your answer using positive exponents only.